Hello there, good evening and welcome. This is your revision show. You're on the Senior High School Revision Show. Thanks for choosing this channel, and if this is your first time, you're very welcome. This is our elective math class, and I am glad to be your guide to help you revise as you prepare, especially if you're in your final year for your WASP. And if you are not in Ghana or some other place and you're following us, you're probably preparing for an exam, which is not necessarily the West African senior secondary certificate exams. My name is Danso. Tonight, I have the pleasure of bringing you another very important topic. We're going to revise this topic together. Well, possibly you have not treated this at all. This would be a good opportunity for you to learn it. And well, you do not have to be a student taking elective math to appreciate this, because it has a very, very strong bearing with core math. Our topic for tonight is vectors. Well, like I said, it has a bearing, and so we'll be treating vectors tonight. What are the things we'll be looking at? Let's look at a sample problem. Let's give ourselves an idea of what this will look like if you are going to be writing the final year exams in the next couple of weeks. Here's a sample problem from June 2018. It is question number 14. It reads, the position vector of points P, Q, and R with respect to the origin are 4i minus 5j, I plus 3j, and negative 5i plus 3j, respectively. If PQRM is a parallelogram, find A, the position vector of M, the magnitude of the vector PM, and the magnitude of the vector PQ. C, the acute angle between the lines PM and PQ correct to 1 decimal place. Our intention is that hopefully by the time this revision class is done, a question like this from 2018, question number 14, you should be comfortable with such a problem. What are the ingredients required? What are the demands of this question? Let's go back to the question. It speaks about the position vectors of 3 points, P, Q, and R. So you need to know what a position vector is. And it says it is with respect to the origin. Well, and they are giving us 4i minus 5j, I plus 3j, and negative 5i plus 3j. What do we mean by the I and the j, and why is it written that way? It goes further to say, if PQRM forms or is a parallelogram, why that plain figure? Why is it introduced? It is because the moment you have a parallelogram, then something about vectors will be unveiled. And you notice in the question you were given to start with P, Q, and R. But the parallelogram has something extra. P, Q, R, and M. There is an M. So there is a point M that closes the shape to make it a parallelogram. So that is missing, and you're required to find it. And then you're required to find the magnitude of the vectors PM and PQ. So you need to know something about determining the magnitude of vectors. So the first thing is to note position vectors. It's to know why it's represented as as 4i minus 5j, etc. You need to be able to locate a missing point if that point is a part of other points. You need to be able to determine the magnitude of a vector. And then finally, C, question C says to determine the acute or find the acute angle between two lines, PM and PQ, with an added responsibility of correcting to one decimal place. So you need to find, how do we find the angles between lines? So that is something else you should know amongst others. I have taken the liberty of quoting this question because in your final paper, if you will be writing the West African Secondary School Certificate Examination, which is coming up very soon, then you should know that vectors and mechanics are a whole block that would give you some amount of questions to answer. For example, in the written part, you will have section A, which has 8 questions in all. You would have 2 questions that deal with this section. I mean, vectors and mechanics. In the section B, where you have to choose, there is a whole block of 2 questions. You are at liberty to solve both, in addition with 2 others, one from each other section, or 1 from this section and 3 others from other sections. So it is an important part. In the paper 1, which is the multiple choice section, of the 40 questions there, you would have 6 questions from this particular group of topics, vectors and mechanics. So it's important to know how to deal with them because you have a chunk of marks. By the way, for this particular problem, question 14, you would have a maximum of 13 marks. So if you solve this particular problem completely and correctly, you have 13 out of 52 possible marks in that section. So I believe you know it is something to take pretty seriously. So we have this as a model problem. I shall not solve this problem particularly, but the ingredients of this question, I would lead you to revising them. Once again, you're welcome to the show. This is your revision show for senior high school students and for people like that watching across the world. Wherever you are, I would encourage you, get yourself a pen or a pencil. I prefer a pen, a book, sheets of paper. A calculator might be very handy here. If this is your first time, you're welcome. If you're one of our regulars, thank you for keeping faith. We're glad that you always do so. And we're going to a learning experience. This is your Joy Learning channel. So let's get right down to business. We would look at our key concepts. So we'll be looking at types and properties of vectors. We shall also be looking at representation and conversions of vectors. And finally, we shall look at some arithmetic of vectors. So what are the types and properties of vectors we shall be dealing with? We shall be dealing with position vectors, negative or reverse vectors, parallel vectors, perpendicular vectors, zero and unit vectors. These are the types of vectors we shall particularly be looking at. There will be a few others we would mention. And please note, this topic is a necessary prelude. We must take this necessarily if we must understand subsequent topics like mechanics, where you'll be dealing with statics and dynamics. And I'll show you why in a jiffy. So you need to understand some of these terminologies, and there are quite a bit of them. Don't get overwhelmed by them. They're pretty simple, just that they're quite a bit. Now, let's talk about representation of vectors. We can represent vectors in a number of ways, and we shall look at them. We can represent vectors in diagrams or diagrammatically. We can represent vectors in their magnitude-bearing forms, we can represent vectors as columns or components, and we can represent vectors in their algebraic or Cartesian forms. So these are representations of vectors. So we shall look quite in details about representation of vectors. It's critical. And then finally, we shall do some arithmetic about vectors. So we shall do the basic arithmetic of addition, subtraction, different kinds of multiplications of vectors. We shall deal with a unique one, a unique addition we call the resultant of the vector. And we shall hopefully close up with the dot product or the scalar product. This show is interactive. At some point in the show, I would want to hear from you as I present you with problems that I would hope you'll be able to handle quite effectively. The phone lines will be open. The phone lines will be displayed at the bottom of your screen. 0302 211 705, 0302 211 706. I take them one more time. 0302 211 705, 0302 211 706. I would let you know when you can call in. So let's get to the first one. What is a vector? Well, from your basic tool, you know that a vector is any quantity that has both magnitude and direction. Now, note this, and note it very importantly, that it is a quantity. A vector is a quantity. And because it is a quantity, it must be measured. Every quantity is measurable. But this time around, this quantity has magnitude. And not just magnitude, it has direction. Let's look at some examples of vectors. So weight, velocity or its companion acceleration, force, magnetic field intensity, and a host of others are examples of vector quantities. We have scalar quantities in contrast. So for example, time is a scalar quantity. So you could say, I have spent an hour. You have measured a duration of time. Now, it is scalar because all we need to know is that quantity. But something like weight is not only a quantity with quantifiable measurement, it also has a direction. Weight, in contrast to mass, is explained this way. A mass is just how much substance a body carries. If you were doing chemistry, your chemistry would deal with things like the molar mass or moles, mole concept. Well, here, the mass is just how much substance it contains. But weight is the direction in which that mass is acting. Generally, weight acts vertically downward, so it acts southward. Velocity, in contrast to, say, speed. Speed is how fast is the body moving. So, for example, you can tell the speed of a car, but you know the speed of a car will tell only how fast the car is moving, but there is something it doesn't tell you. It doesn't tell you where the car is moving. Velocity, on the other hand, which is a vector quantity, will tell whoever is measuring that, yes, this car or this person or this object is moving at this speed, but in so and so direction. So you could move 20 kilometers per hour to the left or 20 kilometers per hour upward. So the direction in addition to the speed gives us the velocity. Same with acceleration, same with force, magnetic field intensity, and a host of other vector quantities. And since they are quantities, then there can be an arithmetic about them. In other words, you can add them, you can subtract one from the other, you could multiply. Well, because it is a vector, you will not multiply the same way you would multiply a scalar, because this time around the direction needs to be taken into consideration. So those two key things or three things. First of all, that it's a quantity, which means it's measurable. It has magnitude, which is the measure of the quantity, but more importantly, that it has direction, are three major things to keep in mind all the time as you deal with vectors. Indeed, it is the reason this topic must precede your statics and dynamics class, because for a static or dynamic body, the body is going to be acted upon by forces, and it is also going to exert forces. And force, like you can see here, is a vector quantity. I hope that is appreciated now. Great. So if you must deal with a body static or a body moving, then you need to understand the vector behavior of the body and of its movement. All right, now that we have the definition, let's look at types of vectors. There are a number of them, like I said. You do not need to memorize them. You just need to understand how they operate. So we have coplanar vectors. Now, these are vectors, sometimes, well, usually for our purposes, they'll be forces. They'll be forces that lie or operate in the same plane, reason for which they're called coplanar. So they are companions in the same plane, coplanar, in the same plane. What is a plane? A plane is an infinitely stretching space. So for example, the XY plane, it is infinitely stretching. So forces that act in the same plane, say XY, will be coplanar. We have collinear vectors. These force vectors, they move along the same line. That's why they're called collinear. They are in the same line. So they're companions along the same line. We have co-initial vectors. Co-initial vectors are vectors that operate from the same point. They are initiated from the same point. So for example, we have vectors, for example, mx and my. Both of them emerge from m. So from m, the other moves to x. From m, the second moves to y. So they are co-initial. They came from the same point. They are initiated from a common point. Then there's the displacement vector. The displacement vector is a vector formed where a point is moved from another point. So that would be a displacement vector. Well, a few more. And we shall encounter some of them in our calculation. So equal vectors. An equal vector is a vector or vectors that have same magnitude and same direction. So if we say two vectors are equal, then they have the same magnitude and they have the same direction. Negative vectors. Negative vectors may have the same magnitude, but they have opposite directions. One is moving left, the other is moving right. One is moving up, the other is moving down. One is moving northeast, the other is moving southwest. One is moving northwest, the other is moving southeast. They are directly opposite each other. They are very important vectors. They help us to balance our things. You'll find out in our mechanics revision. So they are in opposite direction. Position vectors is the position of a point or a vector in relation or in reference to the origin. You remember our sample problem? It asks for the position vector of M. So it's trying to find out what is the position, the location of M with respect to the origin. So that's a position vector, the position of a point or a vector in relation to a reference origin. It's not always the known origin 0, 0. It could be with reference to something else. Okay, the unit vector. As the name implies, the unit vector is a vector that has a magnitude 1. It may point in any direction. Very important, it gives us the behavior of a vector. The moment you can tell the unit vector of any vector, we can, to a very large extent, determine the behavior of the original vector. It is like determining or finding a cell of an organism. The moment you have the cell, you can tell the behavior of the organism. If you can pick an atom of an element, you can largely predict the behavior of the element. So the unit vector helps us largely to determine the behavior of a vector. And then we have the zero vector. The zero vector is a vector whose magnitude is, you can guess, 0. Well, a very interesting fact about it is its beginning is its end. So it's more like a dot, just 0. It has 0 magnitude. So these are types of vectors. Now you need to get used to these terminologies because as we get along, they will be used quite often without necessarily explaining what they are anymore. So I hope you remember coplanar, collinear, co-initial, displacement vectors, equal vectors, negative vectors, position vectors, unit vectors, zero vectors. There are a host of others. For the purpose of this class and at your level, this is how much you really need to bother yourself about. But let's look at how they show themselves diagrammatically. So on your screen, you have 3 vectors, RS, FG, and BA. Now you notice I did not say AB, and I'll tell you why. Now, all 3 vectors, RS, FG, and BA, at least by eye, you can tell that they are all kind of parallel to each other. Well, there is a green dotted line on your screen whose ends have the letters LL. Well, all 3 vectors seem to be along that line LL. So because they're along the same line, we say those vectors are collinear. In other words, they're companions along the same line. Right. Then we have, say, point C on your screen to the right in blue. Now, if we have vectors emerging like you have on your screen, vectors P, CP, CR, and CQ are called co-initial vectors. Why? Let's take a reverse trip. So they're called co-initial because, as you can see, they emerge from the same point. They are co-initial. From C, they all spread out to P and to R and to Q. So they are called co-initial vectors. In our statics class particularly, this will become very important. So please keep this in mind for our future encounter. So let's deal with the equality of vectors. We say 2 vectors are equal if they have, first of all, the same length and direction, and their corresponding components are equal. So, for example, we have vector ST and vector JK. These 2 vectors are, first of all, you notice they are pointing eastward. So in that sense, they are equal. But that's not all. If we took a measurement, you would find out that they are of the same length. Since they are of the same length and point in the same direction, we say vectors ST and vector JK are equal vectors. You notice that we have arrows above ST and JK to show that they are vectors. Please never write a vector without the arrow over it. Indeed, don't just draw a line. If you drew a line, it will no longer be a vector. It will just simply be a line. So it will be called line ST. Well, you need to learn to do that right all the time. Even if it will be overlooked, please learn to do it right. So there should be an arrowhead. And I mean this and that. So the arrowhead must be there all the time. Don't simply draw a line or omit it entirely. Right. But we have 2 other vectors, LM and ML. You notice I didn't call it LM. I didn't call the lower one LM. I called it ML. Why? Notice the direction of the arrows. The first one begins from L and the arrowhead ends at LM. The other one, the tail is at M while it ends on L. They are of the same length, quite all right, but they are not in the same direction. So vector LM is not equal to vector ML. So when two vectors, they may have the same magnitude or the same length or modulus, but if they point in different directions or they have opposite signs, they are not equal. They may have the same magnitude, but they are not of the same direction. All right, position vectors. So we say the position vector is the position of a vector relative to a reference point. So let's say we have our XY plane, and we have 2 points P and Q, as you can see on your screen. Now we can tell the position vector for P and of Q in relation to the origin 0, or O as some people prefer to call it. So the vector OP could be called simply P, small letter p. So usually we'll either denote it by two capital letters, say OP, or by a small letter P. Now it doesn't have to be P, Q, R or anything. It could be any other thing, and you will see shortly. So that is the position vector for OP. Well, but we need to describe it because point P has coordinates. Remember? Yeah, every point has coordinates. On the XY plane, it will have an X coordinate and a Y coordinate, the ordinate and the abscissa of. So it will have coordinates. Same with point Q. And so we have two position vectors, OP and OQ, but in relation to each other. So first of all, P was in relation to the origin 0. Q was also in relation to origin 0. But we can relate P to Q and Q to P. So we can have PQ, which is another position vector. That is the position vector of Q with respect to P. If we reversed it, it would have been QP, which would be the position of P with respect to Q. Now, how do we put all of these together? Now, since we have OP, OQ, and PQ, we say that OP plus PQ gives us OQ. Why? Why that order? Why not some other order? For example, why not OQ plus QP equals PO? Why not that? Well, there's a simple rule, and please get this rule. The rule is that when we are trying to sum vectors, which is already getting into the arithmetic of vectors, what we do is that we must follow the direction of the vectors as though the vectors were, in quote, chasing each other. What do we mean by that? Look at the screen very carefully. You would notice that the arrow from O to P is pointing that way. And then from P to Q, it appears the vector P is chasing vector R. So it's like you moved from O to P and continued from P to Q seamlessly. So we have OP following PQ. Since they are following, you must always add them in that way. Now, imagine we try to do it the other way around. Let's say OQ and then QP. You will notice OQ is moving, but if it was coming down, it will collide with QP. So you cannot add it that way. You must add them in such a way as though the arrows were following, or if you like, chasing each other. So OP seems to be chasing PQ. And then OQ seems to be the closure. It seems to be closing that pursuit. So we say OP plus PQ equals OQ. Since we wanted to find the position vector of Q with respect to P, that is PQ, we can make PQ the subject there. But before we do that, we can say that that will be, by change of subject, OQ, vector OQ, minus vector OP will give us vector PQ. But remember that we had denoted them by small letters. So PQ, which is R, will be equal to OQQ minus OPP. Now, this is a basic rule in vector summation, or if you like, the resultant of a vector. So a few more examples. In general, if you had a vector xy, it would simply be OY minus OX. If you had a vector AB, it would be the same thing as OB minus OA. Now, take a step backwards. You will notice that PQ was OQ minus OP. XY is OY minus vector OX. And vector AB is vectors OB, position vector OB, minus position vector OA. You will notice it appears to be the second minus the first. Please do not simply write B minus A, unless the B means small letter b representing the vector OB. Do not simply write Q with an arrow over it, unless you mean small letter q, which may be the representation of OQ as we have in this case. So do not write a single capital alphabet. It can be a small, single, lowercase alphabet, that's fine. But if you want to represent it using two capital letters like we have done for most of the situations, then please do not write only one capital letter. That would be wrong. That would be a wrong representation of position vectors. In other words, position vectors are represented either using two capital letters with an arrow over them, or a lowercase letter representing that section and no arrow over it. I hope that is clear. And remember, if you're given the vector WD, then it is OD minus OW. If you're given another vector, say YZ, then it is OZ minus OY. I hope you get that now. That's just basic principle. So that's position vector. All right. Now let's talk about the negative, reverse, or opposite vector. A vector is the negative, the reverse, or the opposite of another if they have the same magnitude, but they are pointed or they are headed in opposite directions. So, like we said before, look at vectors ST and KJ. You notice that they may have the same magnitude, they have the same length, but they are pointed in opposite directions. In other words, these two vectors, ST and JK and KJ, are opposite. However, you could make them equal by simply reversing the alphabet. So you could say that ST is equal to the negative of JK. You get the idea now, because ST is not equal to JK in terms of direction. Magnitude maybe yes, but direction no. So it is negative JK. In other words, if you reverse JK, it will be the same thing as ST. Let's take another example. We have LM and ML, same magnitude, same length, but they are pointed in different directions. L towards M is moving eastward, ML moving westward. In other words, like the first case, vector LM is equal to negative of vector ML or LM. So they are in opposite directions. All right. Now let's do a bit of calculation now. Since we now know that the opposites of or the reverse of a vector is when they are in opposite directions. Okay, so we have a vector position. So let's say we have a line AB, and the coordinates of the line AB are x subscript 1, y subscript 1, and x subscript 2, y subscript 2. Well, I'll give you numerical examples, but let's take the concept first. So let's say we have a line like that, and along that line we have a point P whose coordinates are x0, y0. Now, and the moment we have that kind of a point, a number of things are possible. One of it is that that point would divide the line AB into a given ratio, say mn. In other words, we could say that the point P is dividing the line AB in the ratio AP on BP or PB in the ratio m is to n. Now, if we did a cross multiplication, first of all, you know that AP, the vector AP, if we consider that as a vector, it could be denoted as OP minus OA, and BP or PB can be denoted as OB minus OP. Since that is true, if we did our manipulation right, we would have the position or the position vector P to be given as m multiplied by b, and I'll tell you what that b means, plus n multiplied by a, all divided by the sum of the ratios m plus n. Well, b and a would be the position vector or the points, or let me say it in proper order. The points B and A will be, this B and this A will be the positions for B, x2, y2, and for A it will be x1, y1. So if we have any line and we are dividing, especially internally, in a given ratio, say m on n, then we can locate the point this way. If we were dividing externally, it will be simply the same formula, except that instead of plus you would have minus, where m has to be the greater ratio. So for example, if m were 5 and n was 2, then it would be 5 minus 2. All right, let's take an example. Say we have a line, point A 5, 7, and point B 7, -1, and there is a point between those two lines, P, which divides the line in the ratio 5:3. How do we determine the exact location of point P on the line? By our initial formula, we'll have AP on PB being equal to 5 on 3. So 5 multiplied by B plus 3 multiplied by A divided by the sum of 5 and 3, sum of the ratios. Now, what was B? B is 7 minus 7 -1, which we could write as 7i minus j. Now, if that particular notation confuses you, just wait a minute, we'll deal with it. Plus 3 multiplying 5i plus 7j. Another way to have written this, of course, would have been to say 7 -1 and 5, 7. We shall speak in more details very shortly. So we could have done the multiplication by saying, this calculation, we could have said 5, 7 -1 plus 3, 5, 7, all divided by 8. We could have done it that way, but look at the first way we're doing it. All right, so just so that we follow inconsistency, let's solve it using what we already have. So when we do the calculation, 5 by 7 is 35, so we have 35i, then 3 by 5 will give us 15. 35 plus 15 should give us 50. So sorry for that error here. This ought to be 50, not 40. And then you have negative 5 multiplied by negative 1 is negative 5. 3 by 7 is 21. If you added negative 5 to 21, you get 16. And so if you divide it, you should have, this would change obviously to 6.125i, because you have 2 on 8, oh sorry, 6.25. 1 second there. So this gives you 6.25. 6.25i plus 2j, because 16 on 8 gives you 2. So we have been able to locate the point P, which was initially simply x naught, y naught. We now know that point to be 6.25, comma 2. In other words, if we locate a point on the line AB such that the point is at 6.25 and at 2, it would divide the line AB exactly in the ratio 5:3. So please keep this formula in mind. Keep it in mind. Store it somewhere for use. You would be needing it quite often when you have to divide lines in a given ratio. I hope this was pretty clear for you. All right, we shall make some more progress. The unit vector, we talked about it and we said it has a value 1. Well, but not just 1. How do we know it has a value 1? There's a small equation you need to put there. So the unit vector is given by this equation. A hat, so the hat is that sign over the A. It doesn't have to be A. It could be the unit vector of a vector, say, R. You would write R hat. R hat, or the unit vector, is given by 1 divided by the modulus, the length or the magnitude of the vector A, multiplied by the vector itself. So a new concept has been, 2 new concepts here. First of all, the unit vector. The second is the magnitude of the vector. And I used 3 words to speak about the magnitude of the vector. I said magnitude, I said modulus. So magnitude, modulus, and length. These 3 words are used interchangeably because they're synonymous one with the other as far as the magnitude or size of a vector is concerned. So if you ever saw in your tests, in the exams, find the modulus of a vector, please don't be confused. If you saw length, it will mean the same thing as magnitude. Same process to solve them because they mean the same thing. All right. So how do we find the unit vector of any vector? Let's use the formula. Of course, because A hat is equal to that, if we did a cross multiplication, A hat multiplied by the magnitude, you give you the vector itself. So if you were given the unit vector of a particular vector and its magnitude, you can go back and generate the vector itself. So there are 3 things there: the magnitude, the vector itself, and the unit vector. Given any 2, you can find the third. So if you have the magnitude and the vector, you can find the unit vector. Indeed, if you only have the vector, you can find the unit vector. And so by change of subject, you can do lots of things. Okay, so now let's do an example. So let's say we have a vector A given by negative 6i, and please be patient with me. We'll deal with that notation you see, I and j things. We'll deal with it. By the way, the I and j is a unit vector. Yeah. So I just let the cat out of the bag. The unit vector I is the vector along the x-axis. It's a vector with a magnitude 1 acting along the x-axis, while the unit vector j is a vector with magnitude 1 acting along the y-axis. I guess that is given away now. So that's why we call it I and j. Okay, so if we had a vector negative 6i minus 8j, which we could have written as negative 6, negative 8 in a column form, and we'll talk about that. And we were required to find or determine the unit vector of that vector A. What would we do? Look at the formula very well. We're going to do two things. We're going to find the magnitude and then we'll multiply by the vector itself. So how do we find the magnitude of a vector? Simple. Take each of the components, say negative 6 squared. Take negative 8, square that as well. When you have squared both, sum them, add them. When you have added them, find the square root. So the magnitude of a vector, if you want a definition, I mean a mathematical definition or its procedural definition, it is the square root of the sum of the squares of the components of a vector. That is quite a mouthful, right? Yeah, I understand. Let's take it one more time. It is the square root of the sum of the squares of the component parts of a vector. Now, I've said this because for those of you who will pick engineering or allied or something close to engineering in your further studies, you would meet components of vectors beyond x and y. These are x and y, so you have I and j, which are the unit vectors in those directions. You could meet I, j, k, because you could deal with 3 dimensions, even 4 dimensions, I, j, k, stuff like that. All right. So what's the magnitude in this case? Negative 6 squared is 36. Notice I have put the negative 6 in parentheses, in brackets. Please, if you're using your calculator, this is something to take very seriously. Do not simply type negative 6 squared on your calculator. The answer it will give you will be negative 36. As far as the calculator is concerned, that will be correct, but it will be wrong because the calculator has misunderstood you or did not understand what you really intended to say. It doesn't have its own intelligence. So please, whenever you're going to square numbers, please do well to put them in parentheses. Even if it's not a square, the moment you have an order, a power, please put them in parentheses. It's safe, and you know it's better to be safe than to be sorry. So put them in parentheses. Negative 6 squared is 36. Negative 8 squared is 64. 36 plus 64 will give us 100, 100. The square root of 100 will be 10. Well, this particular vector was measured in Newton meters, a force of a kind. So its magnitude is 10 Newton meters. Now, so what is the unit vector? We have been able to deal with the magnitude part. That is the A with the 2 lines by it. That's the modulus, the magnitude. Now we need to multiply, which is the second thing we're going to do, by A. So we're just going to substitute. The magnitude, the unit vector A will be 1 divided by 10 multiplied by negative 6i minus 8j. You could leave your answer simply this way and you're okay. If you intend to simplify it further or you're demanded to do so, then you may. So negative 6 on 10i minus 8 on 10j, which effectively in decimals will be negative 0.6i minus 0.8j all Newton meters. So this is the unit vector of the vector negative 6i minus 8j. You would notice if you squared negative 0.6 and added it to the square of negative 0.8 and you found the square root, your answer will be 1 Newton meter. And you can try that on your own. So it has a magnitude 1. I hope this is clear. Well, let's make some more progress. Now let's deal with the direction cosine. What is a direction cosine? Now these are normal multiple choice questions you would encounter. Not the definition, but more the calculation. The direction cosine is the cosine of the angle between the angle subtended by the line and the coordinates, or if you like, the axis. So if you have a 2D or 3D space, a line would normally, like you remember in your core math, circle theorem, right? They would say the angle subtended by a chord at the center of a circle is twice the angle subtended by the same chord in the same segment, or in the same segment as the chord. So if the angle at the center is, say, 100 degrees, then the one on the circumference should be 50. Now, lines like the chord will subtend angles. So the angle subtended, the cosine of the angle subtended by any line made with the axis x, y, z, depending on if you're dealing with a third angle, is the direction cosine. It's important. It helps especially engineers to determine a lot of things. So what's the direction cosine by calculation? If we have a given vector, say r, which is given by xi plus yj, the direction cosine is, as you see on your screen, x divided by the square root of the magnitude of the vector. And the direction cosine for y is y on the magnitude. So all you need to know is the magnitude, and then x divided by that magnitude, y divided by the magnitude. That will give you the direction cosine. Of course, there are other ways of doing it, but for now, just take this. It's a simpler way. So if you're given any vector, all you simply do is find its magnitude, and we've learned how to find the magnitude. The formula is what you have on your screen, x squared plus y squared, the square root of that. And so let's take an example. So we have the vector, say r, given by 6i plus 8j. Well, for information, I have picked 6 and 8 simply because it gives me the Pythagorean triple, 6, 8, 10. So it's easy to work with. It could be something else. If I was supposed to find the direction cosines for this, then I need to find the magnitude first. The magnitude will be 6 squared plus 8 squared, which will give me 100. Square root of 100 will be 10. So all I simply do is I'll say 6 divided by that 10 and 8 divided by the 10. 6 divided by 10 is more like saying 0.6 or 3 on 5. And 8 on 10 is more like saying 4 on 5. So it could be written in terms of its decimal as 0.6 and as 0.8. These two are the cosines of the angle formed by that vector r relative to the dimensions x and y. So we can find the angle between x and y if we wanted to by simply finding the arc cos or the cosec of those angles 0.6 and 0.8. It means that cos or the cosine of a certain angle gave us 0.6. So the arc cos or the cos inverse of 0.6 will give us the angle. Same with 0.8. So these are the direction cosines. Quite simple, not so. Just find the magnitude of the vector, and then for x divided by the magnitude, for y divided by the magnitude. Quite simple and straightforward. Okay, now let's talk about the projection of one vector on another. And after this, hopefully, we shall be able to do a few things together. What is the projection of a vector on another? I want you to think about it this way. Think about, say, a pole, a telephone pole, an electric pole, any kind of vertically standing object. And imagine that there isn't too much light around you. So you flash some light from maybe a touchlight on the pole. Now you would agree with me, well, even if it's your friend, just make sure you're not flashing the light in their faces. You would notice that it will cast a shadow on the opposite side, not so. All right, often we want to be able to tell what a vector's effect will be on another vector, almost like domino effect. When you push, what is going to happen? we try to be able to predict that. So the projection of one vector on another vector is to find out, if you like, the length or the magnitude or the effect of that vector on the other vector. So that is a projection of one vector on another. Well, so we have vectors x and y on your screen. If I want to find the effect, the shadow, the length of that vector on y, well, it has an angle between, obviously. So I could call that OA, so that the projection of x on y is OA. In that regard, the scalar projection, and you notice the word is underlined, scalar projection of x on y is given by that equation, x dot y divided by the magnitude of y, because it is on y. We could have the projection of y on x, in which case it would be y multiplied by x divided by the magnitude of x. I'll take that again. The projection of x on y, as we have in this case, is x, the vector x, multiplied by the vector y, divided by the magnitude of y, because we said on y. If we had asked the projection of y on x, then where you have y, it will change places. You have x there. So it will be y multiplied by x on the magnitude of x. Now, if you look carefully, you would notice that this side is the unit vector of y, because unit vector, we said earlier that a hat is 1 over the magnitude of a multiplied by a. That is the vector a. In other words, y hat is the same thing as y on the magnitude of y multiplied by the vector y. So that circled area in the formula is the same thing as y hat. So it is the same thing as saying x multiplied by the unit vector of y. So if you are asked the scalar projection of one vector on another, or what do you need? You would need the two vectors, x and y. So you multiply x by y, and then you divide by the magnitude of y. And the same if you had to do the scalar projection of y on x. Okay. But there's also a vector projection of x on y. It is a continuation of this. Now, in the first case, it was a scalar projection. So your final result will simply be a scalar quantity. The vector projection will tell us not only how much effect it has, but in what direction it is going. So it is the result from the first multiplied by the unit vector y. So you multiply a second time. Let's take an example to get all this home. So given two vectors x and y as 13i plus 6j and y as 4i minus 3j, the projection of x on y, the scalar projection that is given by 13i plus 6j multiplied by 4i minus 3j divided by the magnitude of y, 4 squared plus negative 3 squared all square root. If we did the multiplication right, we will have 38 on 5, which will be 7.6. So that is its scalar projection of x on y. How did we get the 38? I'll show you in greater details later, but suffice it to say you simply multiply 13 by 4, which gives you 52, and then you have 6 multiplied by 3, negative 3, you get negative 18. So I simply multiplied this by this and multiplied this by this, and I summed it. Why didn't I do the rest? You'll get to see later. So 4 by 13 gives me 52. I'll get 52. 6 by negative 3 gives me negative 18. 52 minus 18 should give me, 34. 34, I beg your pardon. So this should be 6 point something. All right, but you get the calculation. 34 on 5 will give us 6.8. So that is how we deal with that particular matter. Now, what about the vector projection? The vector component will be all of what we did multiplied by the unit vector. Remember, this is the unit vector. So we just simply multiply our final answer there, which should have been 6.8 really, by what we now have there. So that is a projection of one vector on another. All right. We shall take the resultant of a vector, and when we are done, we take a break. When we come back, we will do a few more things. So let's deal with the resultant of a vector. What is the resultant of a vector? It is, like the word implies, the result of vectors. So it is like the sum of vectors. Now on your screen you have vectors PQ plus vector QR equals PR. Remember what we said? OP, PQ is OQ minus OP. Now look at it. PQ plus QR equals PR. We call that R subscript 1. Now, why is it so? Now we have a vector PQ. If it chases another vector QR, remember what I use chases. So you see, from P to Q, it begins from P, ends at Q, but Q now is a fresh beginning, ending at R. Then the resultant of these two vectors, PQ and QR, will be PR. So PQ plus QR gives us PR. So R1 is called the resultant, or if you like, PR, vector PR is the resultant. It's the sum of the vectors PQ and QR. Now, what if we had to add some more? So we have PQ, we have QR, and then we had PR. We have summed it. Now, what if we extended from R, the vector was moving? So when we say vector, imagine there is a movement. Somebody walked from point P to point Q. Then he turned from Q to R. What is the total distance is covered in terms of vectors? You could say PQ plus QR, not so, yes. But it simply means he has moved from P to R. You get the point now? So you move from P to Q, and then from Q to R. So I have said you have moved that distance. Think of PQ and R as towns or cities or places, locations in a space. So it means you've simply moved from P to R. That is the summary of it. You moved from P to R. Although you had actually moved from P to Q and then from Q to R. But in summary, which is the resultant, we say you've moved from P to R. Now, what if you move from R to, say, a point S? Then it means you have moved from P to Q, Q to R, and R to S. In summary, you have simply moved from P to S. That's the resultant. So you see how it moves. The arrows must chase each other. So PR was chasing RS, and it was closed up by PS, which is our resultant R2. This is what we call the resultant of a vector. And we call this the polygon way, or the polygon summation of vectors. We'll take a break at this point. When we come back, we'll do a few more concepts, and I would invite you to call in and let's have a chat. I'll see you after the break. Please stay with us.
Week 4, 5, or 6? Hop onto the Joy Learning vehicle and enjoy a free ride with no stress at all. Our sweet English facilitator, Eva Brobe, will help you understand the English language with no worries. IT guru Peter Asamoah leaves no topic unturned in ICT. Our ever entertaining Emmanuel Kwesi Adi has the key to your mathematical problems. All these programs come with no cost at all. It is absolutely free. Yes, you heard right. It is free. If you miss out on any of our TV lessons, you can access them on our YouTube channel at Joy Learning. For more updates on our programs, follow us on our social media handles: Twitter, Facebook at Joy Learning TV, and Instagram at Official Joy Learning TV.
Examination malpractice is any form of deliberate cheating on examinations which provides one or more candidates with an unfair advantage or disadvantage. It is an illegal act and can be perpetrated by a single individual or groups. It can occur outside or inside the classroom. So before you enter the exams hall, make sure you follow these instructions. 1. Empty your pockets and avoid entering with a foreign material. That is smuggling of answer scripts. 2. Avoid writing on sheets of papers, handkerchiefs, erasers, covers of calculators, and on the skin. Remember not to fall victim to any examination malpractices so you could have a peaceful examination. Prepare well, and we wish you all the best. Joy learning. Keep learning.
Are you a learner? Joy Learning has got you. Grab your learning materials and join our junior high class with our tutors who are always on standby to help you with your educational journey. Are you scared whenever you see figures? Worry no more, says Samuel Okwabi has made mathematics easy for you. Is it a phobia of science? Sir Bismarck Opokunyako will heal that disease in just a twinkle of an eye. Have you heard about Jacqueline Kunedu, the most adorable English facilitator? You don't have to stress about the English language at all. How about religious and moral education? Oh, Madam Rachel Ousu Ampoma got you sorted out. Your social studies class is never dull when you have Madam Anita Ochre as your facilitator. Do you wish to become an IT guru? Sir Isaac Amankwa will make that dream come true. All these lessons are offered at no cost. If you miss out on any of our TV lessons, you can access them on our YouTube channel at Joy Learning. For more updates on our programs, follow us on our social media handles: Twitter, Facebook at Joy Learning TV, and Instagram at Official Joy Learning TV. Joy Learning, keep learning.
You're welcome back. Nice to have you with us. If you just joined us, we have been studying or revising vectors, which is a necessary prelude to mechanics. So far, we have been able to touch base with a number of definitions, a number of very key concepts. And this time around, we are continuing with the resultant of a vector where we ended. We're able to tell that when the arrows chase each other, we can summarize it using the beginning and the end. So PQ plus QR is PR. PQ plus QR plus RS is simply PS. So the beginning till the end. So we simply ask, where did you start from? Where did you end? And basically, that is it. All right, let's do something else. We're still dealing with resultants of a vector, but this time around, we're going to deal with the parallelogram. You would recall that in our sample problem, we had a parallelogram PQRM. The vertices P, Q, and R were given. M was missing. So let's see how to deal with that situation. Now look at this. So we have PQ as a side of a parallelogram, and we have, let's call it R1, and we have another side, QR. Notice this time around, they're chasing each other. P is chasing Q, Q is chasing R. And we call QR R2. Now, we can do something about these two things. First of all, since they are adjacent to one another, in other words, the lines are next to each other and they are joined, something necessarily will happen. There will be an angle between them. You may have learned very basic rules that wherever there are two lines, there are angles. Yeah, well, it's only with a caveat that the two lines meet. Well, if they don't meet, the angle between them is 0. All right, so there will be an angle at Q. But since they are the way they are, we can create something. So watch. We can create a line parallel to PQ, and we can create another one parallel to RQR. If we completed that, we would have formed a parallelogram. The dotted lines were not originally there, we created it. So if we have two vectors, which could be two weights, two magnetic field intensities, two accelerations, two velocities. Remember, they are quantities, right? We could represent them with the two sides of a parallelogram, assuming that they are co-initial. In other words, they are from the same source, or they are coplanar, they are in the same plane. Remember? Okay. If this is true, then we can use our earlier knowledge that when they are chasing each other, for example, P to Q, and then from Q to R, then the summary will simply be PR, not so. Yep. So the diagonal of the parallelogram would then be the resultant of the vectors PQ and QR. Just straightforward. So we say that R, which is the resultant PR, will be the sum of R1 plus R2. So let's just bring a few relationships here. PQ, the vector PQ, is parallel to SR. We know that. PQ is parallel to SR. It also means, since it is a parallelogram, the property of a parallelogram is that opposite sides are parallel and opposite sides are equal in length, like a square, a rectangle. For a rectangle, opposite sides are both parallel and they are both equal. A rhombus, both parallel and equal. So they're all parallelograms. Of course, a kite will not obey that, neither will a trapezium, because they are not parallelograms. All right, so their magnitudes will be the same. In the same way, the vectors QR and vector PS will be parallel, which means since it's a parallelogram formed, then their magnitude QR and the magnitude of PS, which is R2, will also be the same. Well, that being the case, we can say PQ plus QR is PR, which gives us R as the resultant. It will be the same. Now, you notice I keep using the word the same, the same. That brings us to that concept, equality of vectors. They must be in the same direction. They must have the same magnitude. So, PS plus SR must also give me PR. All right. Now that we know these things, keep them in mind. Keep these in mind. That the moment you hear that two vectors meet, you can make a parallelogram out of it. If you're asked to find the resultant of that vector, you could use these relationships. That, okay, since PQ is parallel to SR, then they must have the same length and they must be parallel. QR is parallel to PS, and since it forms a parallelogram, then they must have equal length. And so using these relationships. If you know some of it, you can find the others. That's simple. Okay. Now let's deal with representation of vectors. I promised I was going to touch on that, and we'll do a bit of calculation here. Now, vectors, because they tell us about the quantity and their direction, we can represent them in a number of ways. First of all, we can represent them using diagrams or arrows. And so the length of the arrow tells us its magnitude, the direction tells us where it is going. So xy, the length of xy is not the same length as AB. So if we had a scale and we're measuring to scale, we can say that the vector AB has a greater magnitude than the vector xy, although they are pointed in the same direction. So yx is not the same thing as xy, because yx is pointing in the opposite direction, same as BA, which is pointing in the opposite direction as AB, although they have the same length approximately. That is one way of representing vectors. Now, we can also represent vectors based on their magnitude bearing. Remember, every vector has a magnitude and it has a direction. The magnitude is the magnitude part of the representation. The bearing part is its direction. Remember, bearings are measured from the north and they are measured clockwise. What do you mean by clockwise? The way your clock ticks, it moves that way. So from 12, it goes to 1, to 2, to 6, to 9, back to 12, and in that order. That's a clockwise direction. So if you have a vector like this, 62 newtons, 005 degrees, then you have described the vector as its magnitude and bearing. You notice I did not write 5 degrees. I wrote 005. It's not fanciful. It's the convention and acceptable way of writing a vector. It must always be in 3 digits, even if it was just if it was just 5 degrees. Even if it was just 1 degree, you would have to write 001 degrees. In fact, in some cases, they would even write 005 degrees capital T to show that it was true bearing, because it is opposed to what we would call compass bearing, where you measure northeast, northwest, southeast, or southwest. Well, so that is the magnitude bearing form. We could also write, for example, you could also write 12 meters per second square, which is acceleration, and 021 degrees. So you notice, although it is 21 degrees, I did not write 21. I wrote 021, because it must always be in 3 digits. Then we could also represent it as a component. In other words, I could write it in a column form, which you're probably used to, xy. All right, so this is a component form. Now notice there is no line between x and y, so it is not x divided by y or x over y. It's simply xy. And then you could represent it in the Cartesian or algebraic form, which is what we have used quite a lot today. AI plus bj, where a could be any number, 3, 4, 5, anything. So these are the representations of vectors. Now, what this means is, if we can represent a vector in one way, we should be able to convert that representation to another form. So for example, if I had it as magnitude bearing, I should be able to convert it to a component or column form. If I had it in the column form, I should be able to bring it back to the magnitude bearing form. We're going to do those calculations briefly. All right, so an example of the Cartesian form is, say, negative 2i plus 9j. That's what you kept seeing much earlier. It is a simple way of writing it because, I mean, it's simple. You don't have to write too many things. So instead of writing, for example, in this case, negative 2, 9, which takes quite a lot of space, you simply write negative 2ij, and you're fine. Remember that I and j are unit vectors in the x and y directions respectively. Okay, so let's do conversions. Let's convert from magnitude bearing to component. And now please watch this very carefully. It's pretty simple, pretty straightforward. And I will be testing you after this. So the phone lines will be open and you'll be able to call in 0302 211 705, 0302 211 706. So please follow this carefully so that when the phone lines are open, I want to hear you quickly, aggressively attack these questions. So let's go. We have an acceleration 48 meters per second squared acting in the direction 030 degrees. We are required to convert it to its column, that is XY form. How do we do that? Now, this is what you do. Quite simple. You simply say 48 sine 30 degrees. That gives you the x component, which will be 24.00. I have put it in 2 decimal places. There are times when you are not required to do that. And then for the y component, 48 cos or cosine 30 degrees. Why did I do that? Well, I won't want to bother you with the proof of it. In some textbooks, you would notice that instead of 48 sine 30 degrees, you will see cos 60 degrees. So you have 48 cos 60 degrees and 48 sine 60 degrees. Well, it is because they are not measuring from the north, they are measuring against the east or the x-axis. And that's the reason you have cos before sine. I prefer to use this because it's straightforward and not confusing, especially when the angles become larger than 90. So please, just to make life easy for yourself, don't try converting to the horizontal. So you just simply say 48 sine whatever the angle is, or the magnitude sine whatever the angle. So you simply say magnitude m sine the angle, magnitude cos the angle. You would have converted. Quite straightforward. I like this also because we know from trigonometry that the sine of an angle divided by the cosine of the same angle is the tangent of the angle, not so? So we say sine theta divided by cos theta is tan theta. Why do I like that? If we use this format, then whenever you have to determine the angle, you can simply say tan of what you have here, and I'll show you very shortly. So if we did this conversion, 48 sine 30, we get 24. 48 cos 30, we get approximately 41.57 meters per second square. So this is the acceleration of the body in its column form. It accelerated at 48 meters per second square in the direction 030 degrees. In the component form, it was 24.00, 41.57. So we have converted from magnitude bearing to the component or column. It's called component because they are parts, column because of how it stands. It's standing as a column. All right. Now let's convert vice versa from the component or column form to the magnitude bearing. Let's see what it will look like. So let's say we have that same thing we just solved, 24.00, 41.57, and we're converting to magnitude bearing. What would it look like? Well, our procedure is something we have done before. Magnitude, remember magnitude? Square root of x squared plus y squared. So you square 24, square 41.57, put them together. When you sum them and find the square root, you will get the square root of approximately 2,304, which if you punched on your calculator will be 48 meters per second. But remember, per second squared. But remember, it is magnitude bearing. You have found the magnitude by simply squaring the components, summing them up, and finding the square root. So 24 squared plus 41.57 squared. You could even leave your answer in the said form originally so that you don't have to approximate. And if you find the square root of that, your answer should be approximately 48 or 48.48 meters per second squared. But that is the magnitude. So what is the direction? What is the bearing? That will make us do a sketch. So let's do a sketch. If we did a sketch, we'll have that where we have 24 on the x-axis, we have 24, and then we have 41.57 on the y-axis over there. So notice I said, if you did that, you can simply say the angle between, let's call it tan, so that this was 41.57. So if we are finding the tan of the angle, remember we're measuring from the north or the y-axis, so this angle is all we're looking for. If we say tan alpha, it will be opposite, which is 24, over adjacent. So Katua, adjacent is 41.57. That will give us approximately 0.5773. Now, to find the angle alpha itself, we'll find arctan or tan inverse of 0.5773. That should give us approximately 30 degrees. It will be 29 point something. So you notice we have found the magnitude, which was 48. Now we find the angle, which is given by 30 degrees. And remember, we must write it in 3 digits, so it will be 030. So by conversion, our 24 41.57 meters per second square converted to its magnitude bearing gives us 48 meters per second squared and 030 degrees. I hope you follow this. I'll take another example so that you get it. All right, so say we have another magnitude bearing problem. We have to convert 16 meters per second operating in the bearing 210 degrees to the column form. So you have the velocity of a body, 16 meters per second, and it is in the angle 210 or bearing 210 degrees. What it will mean is this, that if you had our cardinals north-south, east-west, and we're moving in the clockwise direction, we would have moved 90 degrees here because each of them is a quadrant, 90 degrees, another 90 degrees, making 180. But it moved in 210, so we'll need 30 more degrees here. It means the body was moving southwest, south 30 degrees west. That will be the direction. We need to convert this to the column form. From that sketch, you can tell that it will fall in the third quadrant between the west and the south. So what do? Like I intimated, 16 sine 210 degrees, 16 cos 210 degrees. I have left my answer in the third form. Well, you can convert it if you want, depending on the demand of the question. I intentionally left it this way so that you know that it can go either way. My answer is -8 for the x component and -8√3 for the y component, all meters per second. You notice they're all negative, so negative x-axis, negative y-axis. So it's in the southwest region or the third quadrant. So I have converted from magnitude bearing to component. So you see, that is pretty straightforward. You simply you simply multiply the magnitude by the sine of the bearing and the magnitude by the cosine of the bearing, and you would have converted to the column form. Pretty straightforward. So I hope you can do this. All right. What if we were trying to reverse the process? So we have -8, -8√3 column, and we wanted to convert it to magnitude bearing. First of all, we must get a magnitude, and secondly, we must get a bearing. How do we get the magnitude? The same way you would have found the magnitude of a vector, because it is a vector. So what do? You square -8 and you square -8√3. If you are comfortable with your set, you know -8√3 all squared means -8 by -8, which gives you 64. √3 by √3 gives you 3. 3 times 64 gives you 192. 192 plus 64 will give you 256. The square root of 256 will give you 16. So you have 16 meters per second. That is the magnitude. So you are done with one part, the magnitude. You are left with the bearing. To do the bearing, you need to sketch. But you don't always need to sketch, especially if you are working with, on the objective test. There's a clue. The clue is if you know the quadrants. So you know that from 0 to 90 will fall here. And you know that for this second part, it will be 91 to 180. Here you have at least 181 to 270. And there you have from 271, for example, to 360 degrees. So the moment you see 210, you know where it falls. And then you could make life a lot easier for yourself. So after you found the magnitude, instead of sketching and drawing, when you see 210, it's going to be negative, negative. And what's the angle going to look like? So I'll show you. So we have found the magnitude. Let's go find the bearing. So we sketch. You notice my sketch, I have tilted it more towards the left because I know it will not fall on the right. But if you did not know, you could just do a calculation. Where would 210 fall, beginning from the y-axis and measuring clockwise? Well, I know it will fall there, so I have my arrow there. So that arrow signifies the magnitude. What are the components? The components are -8 and -8√3. And it doesn't have to be precise. You don't have to measure. It's a sketch, so don't be precise. The angle I seek is the angle alpha there. I know the other one from y to negative y, from positive y to negative y will be 180 degrees. I know that. But I need to find out from negative y to the arrow, what's the angle? So I do my calculation. I have -8 or -8√3. By the way, just a quick one here. You don't need to put the negatives or the positives. They are immaterial because it will not really give you much information. All it tells you is where it lies. Now that will give you 1/√3 if we did the division right. If we rationalize the third, it will be √3/3. So if we found the tan inverse or the arctan of √3/3, you know that to be 30 degrees. So alpha is 30 degrees. But that is alpha. What we really seek is not alpha. We seek the entire angle from the positive y-axis until alpha. So the bearing will be 180 plus alpha, where 180 is that angle over there. So we have 210 degrees, which is from here all the way, plus alpha. So we now have our magnitude bearing to be 16 meters per second, 210 degrees. I hope you got it now. So, like I mentioned, since we know that it is magnitude sine theta, magnitude cos theta, all we need to do if you want to find the angle is, since we knew this as -8 and then -8√3, all you simply do is you say tan of 8 on 8√3. So this is how you just deal with it, and your answer will be fast. All right. So for the Cartesian form, the moment you can convert to column, all you do is you write I and your j's and you're fine. So 15,0 will simply be 15i plus 0j, or simply 15i. If you had 0.3 newtons, it could, that should be 10, not 12. You could simply write 10i plus 0.3j. So that's not really a big deal. If you had -5, -1, that would be -5i minus j. So those are your conversions. For components to Cartesian or to the algebraic form, it's pretty simple. The moment you can get it to the component form, you're fine. All right. So let's do some exercise here. Now, the phone lines are open. I want you to express this for me in the magnitude bearing form. I have 5 problems on your screen. The phone lines will be advertised at the bottom of your screen. I'll take them: 0302, 211 705 0302 211 706. I want you to convert this to its magnitude bearing form. They have been given to you in their Cartesian form. If you want to first of all convert it to the component form, that's fine. I'll give you an idea. The first one could be negative 12, 5. The second, you could have it as 3, negative 4. The third as negative 8, negative 15. The fourth as 1, 1, because it is I plus j. And the last one as 2, negative 10. Your job is to convert it to its magnitude bearing form. Who is my first caller who is able to convert any one of them to the magnitude bearing form? I give you the hint once more. All you do is you square each of the components, sum them, find the square root. Just that, pretty straightforward. Square the components, put them together. So square negative 12, square 5, put it together, find the square root. That gives you the magnitude. The bearing, notice negative 12 is on the negative x-axis, 5 is on the positive y-axis. So it will be between 271 and 360 degrees. So that angle must be more than 270 degrees. If you did a sketch, you'll find where it is. So find tan inverse of 12 on 5 and add 270 to it. Simple trick. So I'm giving you the clue. In the second case, after you have squared, where would it fall? 3 is positive x, negative 4 is negative y-axis. So it will be between 91 and 180. So find tan inverse or arctan of 3 on 4. Ignore the negative sign. Just find the tan inverse of 3 on 4 and add 90 to it. In the third case, find the tan inverse of 8 on 15 and add 180 to it because it will be negative, negative. So who is calling? Do I have a caller on the line? All right. So I give you more hints. For the fourth one, again, you square 1, add it to the square of the second one, you get a certain value. Then find the tan inverse or the arctan of 1 divided by 1, which is 1 essentially. Since both of them are between the positive x-axis and the positive y-axis, all you need to do is to subtract from 90. And then the final one. Do I have a caller on the line? Hello.
Good evening, sir.
Good evening. Who do I have on the line, please?
My name is Raymond.
Raymond, you're welcome to the show. Where are you calling us from, Raymond?
I'm calling from Wali Wali.
Oh, you're welcome. How is Wali Wali today? Hello, Raymond.
Hello, sir.
How is Wali Wali today?
Oh, it's fine.
Fantastic. Raymond, which of them do you want to convert for us?
Converting the I. The I.
Number 1.
I have the I.
Okay.
So I have 13.
Okay.
13, and the bearing is 293.
Okay, you approximated it to 293.
Yes.
Thank you very much, Raymond. That is correct. So Raymond has answered for us question 1. Raymond, are you still on the line?
Yes, sir.
Raymond, what class are you, if I may ask?
I'm in Form 2.
Oh, fantastic. That's a good one. Raymond, you are correct. So for question 1, our magnitude is 13 units and the direction or the bearing is approximately 293 degrees. Thank you very much, Raymond. You want to try another one?
I'll call back.
Oh, that's great. Thank you very much, Raymond. So Raymond from Wali Wali has helped us solve question 1, and he tells us that he got 13 units and approximately 293 degrees. So That is the conversion. You notice 293 is greater than 270 because by the sketch, it will definitely fall between the negative x-axis and the positive y-axis. So the fourth or the second quadrant, more or less. Yes, do we have another caller? So Raymond has just guided us through the first one. He's helped us solve the first one. We have 4 more to go. Who is helping us? I have done a bit of the work for you by converting it from the algebraic or Cartesian form to its component form. All you need to do is square each of the components, put them together, find the square root. That gives you magnitude. For direction, find the tan inverse of the x on the y and locate the exact place it will be. If you want to do a sketch like I did in the previous calculation, why not? You're free. But you could make it a lot faster for yourself. All right. So our answers, I'll produce them very shortly since our phone line seems to be giving us some challenges. I'll produce the answers and you will have opportunity to try others. Do we have a caller on the line?
Yes, please.
Good evening.
Good evening, sir.
Who am I speaking to, if I may?
This is Timothy.
Timothy, could you raise your voice, please? Timothy, you're welcome to the show.
Thank you, sir.
Why are you calling us from, Timothy? Abo Senior High. Oh, that's my Timothy.
Yes, sir.
Timothy, you're welcome today. Timothy, you seem down. Can I get some vibe in your voice?
Okay, sir.
All right. So, Timothy, which of them are you solving for us?
So please, the question 10, please.
Question 2 and 3.
Yes, please.
Carry on, Timothy. What do you have?
So please, I have 5 units for the question 2.
Okay.
5 units and then 143.13 degrees.
Can you take that again? I did not hear your bearing.
143.13 degrees.
143.1 degrees.
13.
Timothy, I think there's a challenge with the bearing. Tell me how you did it. Let's see. Let's go. Tell me how you did it. Your magnitude is correct. You have 5 units, right?
Yes, please.
Okay. So tell me how you did your bearing.
It will be found in the second quadrant.
Okay. So you have, this is what it will look like. You have 3 there, right?
Yes, please.
And then negative 4 will be down here.
Yes, please.
So you have this angle you're looking for.
Yeah.
So how did you find that?
So tan theta equals 4 on 3.
Tan theta will be
4 on 3.
4 on 3, okay? Which gives you what?
So I took tan inverse and which will give me 53.13.
Okay, okay. So I agree with you on that. Yes, I agree with you.
So I add 90 to that.
You added 90 to it because you're coming from the top, right?
Yes, please.
All right. So your answer was 5 units against what?
143.
143 degrees.
0.13.
Okay, 0.1. Let's leave it at 143 degrees.
Okay.
Okay, thank you, Timothy. What about number 3?
I got
okay, Timothy says we should hold on for him.
I got the unit though, but I got the bearing.
Okay, you got the bearing.
Yes, that's 208 degrees.
208
8.
degrees. You're right. What about the magnitude?
I'm not getting that.
You couldn't get that?
Yes, please.
Okay, so let me help you. Do you have a calculator with you?
Yes, please.
Okay, so do this. 8 squared,
Okay.
or if you like, negative 8 all squared. That would be 64, right?
Yes, please.
So 64, what is the square of negative 15? That would be 225.
55, yeah.
225 plus 64. What does it give you?
Yeah, I evaluate so I got the relative 17.
You had what?
17 degrees.
Yes, because it will be square root of 289, right?
Yes, please.
Good. So you have 17 units and approximately 208 degrees. Thank you very much, Timothy from Abo. Well, we have 2 more problems. I will just give you the summary of the answers. So these are our answers. We do a small correction here. Here we have 143 degrees, approximately. So these are our answers, and you can cross-check it for yourself. Well, I have another set of questions for you. And here, I want you to express the following in the form AI plus BJ, where A and B are the components. So this time around, your job is much simpler than the first case. In this form, all you simply do is 4 sine, 4 cos, 10 sine, 10 cos, and on and on. So let your calculators work very quickly and let's see. But remember, when you finish, you ought to write them in the form AI plus BJ. So our callers, you may do that. I have given the problems to you in their magnitude bearing form, and you are required to write them in their algebraic or, if you like, Cartesian form. So let's see who comes first. This is very quick. You could do this very quickly. So all you do is 4 multiplied by sine of the angle, the magnitude by the cosine of the angle, you get the y component. So magnitude times sine of the angle, you get the x. Magnitude times the cosine, you get the y. Then you simply write it as I and j. So you just run all through that, and let's see what we do, what we have there. Yes, do I have a caller on the line? So we have a magnitude 4065 degrees, question 1. Question 2, magnitude 10, bearing 045 degrees. Question 3, 8.2 magnitude, bearing 120 degrees. Question 4, 18 magnitude, bearing 315 degrees. Question 5, magnitude 40, bearing 270 degrees. Do I have a caller on the line? Do we have a caller? All right. So just to emphasize, all you simply do is magnitude, sine the bearing, magnitude, cosine the bearing. Hello, good evening.
Good evening, sir.
You're welcome to the show.
Thank you, sir.
Please, what's your name?
Yes.
Who am I speaking with, please?
Raymond.
Oh, Raymond, you're back.
Yes.
Raymond, okay, so help us, Raymond.
So, my director, the answer is 3.65i.
3.6.
I said the I component is 3.63i.
Okay.
And the y component is 1.69g.
So it is 3.6i plus
69g.
1.69g.
Yes.
Raymond, that is correct.
Okay.
That is
the
correct.
second one.
The second one. Okay, thank you, Raymond. Let's go.
Yes. The second one is the I component is 5 root 2.
Okay.
Plus 5, the y component is 5 root 2.
5 root 2, j, right?
Yes.
Okay, if you converted that, would be approximately 7.07.
Yes.
Oh, thank you very much, Raymond. You're also correct on that one. Now, Raymond, I want you to watch this. Did you notice that you had both of them as 5 root 2, 5 root 2? Did you notice that?
Yes.
Do you know why? Raymond, do you know why?
No.
Okay, I'll tell you why. It's because the angle is 45 degrees. It's exactly halfway between 0 and 90.
Yes, yes.
Because sine of 45 is always the same thing as cosine of 45.
Yes.
They are complementary angles.
Yeah.
Yes. I like the way you said the year. You got it. Thank you very much, Raymond. All right. Do we have another caller on the line? Raymond has helped us with questions 1 and 2. Raymond from Wali Wali, all the way from Wali Wali, and I'm glad you're following us. Yes. Do we have another caller? All right. So these are some examples, and I just give you the full remit of the answers, and then you can cross-check them at your leisure time or after the show. All right. So these are our final answers. I have converted them from their set form into a more friendly form, and I have approximated them to 2 decimal places. Now notice question 5 was 40 270 degrees. Now sine 270 degrees will give you -1. So negative 1 times 40 will give you negative 40. Cos 270 degrees will be 0. It will be 0. And that will mean 40 by 0 will be 0. So if you had a magnitude bearing or a force or any vector quantity acting 40 degrees 270, then you are talking about a situation where there is no j component. There is no y component. It will be just I. All right. So these are your answers. And that's why the last one has no j. If I wanted to write a j, it would be simply plus 0j, because there will be no j. Same way, if it was, say, 90 degrees, cos 90 would have been 0. So there would have been no horizontal component. It would have been only a j component. There would be no I. So don't let that bother you. It means it is lying on the axis. All right. So let's do vector arithmetic. Now, in adding, subtracting vectors, all you simply do is make them the components. If you had vector A and vector B, given as they are on your screen, x1, y1, x2, y2, and you were adding, all you simply do is add the components, x1 plus x1 plus x2, sorry, and then y1 plus y2. Basically, that's all you would do. And you would have added it. If it was in the Cartesian form, you just pick out the i's, add them, and add the j's. And that would be it. So if you are subtracting, you would do the same thing. x1 minus x2, y1 minus y2. Or in the Cartesian form, you group them like you normally do grouping of terms. So all the i's together. So if you're subtracting vector b from a, it will now be x1 minus x2 and y1 minus y2. Each time you put the i's and the j's. So let's take an example. We have vector a as negative 2, 5, vector b as negative 3, negative 1. If we were going to add them, we simply say negative 2 minus 3, and then 5 minus 1. That is when we have said negative 2 plus negative 3, and 5 plus negative 1. But you know that positive, negative, and negative, positive will give you negative. So you have negative 2 minus 3, and then 5 minus 1. So eventually, a plus b gives us negative 5, 4. If we were subtracting, we can also subtract directly. So we would say negative 2 minus negative 3, and then 5 minus negative 1, which effectively will be negative 2 plus 3 and 5 plus 1. Or if we wanted it to be in the Cartesian form, we'll just group them. And in each case, our answer will simply be I plus 6j, or 1, 6, if we wanted it in the component form. We can multiply a scalar by a vector, and we'll be ending on this note. All too soon, our time is coming off. So if we had a vector A and a vector B, we could multiply it by a scalar k. What do we mean by a scalar k? Any number k will multiply a vector, especially when it's in the component form. If it's in the Cartesian form, then you have to group them separately and then multiply. So just a quick note. Ka and Kb are both parallel to the vectors A and B. Whenever you multiply a vector by a scalar, the new vector you get is parallel to the first one you worked with. So let's take a quick example as we wrap up for today. We have a vector A given by negative 2, 5, or in the Cartesian form, negative 2i plus 5j. If we multiplied it by a scalar quantity 1 over 5, this is what it will look like. We'll be multiplying negative 2 by 1 over 5 and multiplying 5 by 1 over 5. If we did that, negative 2 by 1 over 5 will give us negative 2 on 5. 5 by 1 over 5 will give us 1. If you wanted to convert it to decimal, it would be negative 0.4, 1.0. And that would be our answer just effectively. That's what it would be. So if you're multiplying a scalar by a vector, that is what you do. You simply multiply each of the components by the scalar. So for example, if instead of k being 1 over 5, we had 5, it would be 5 times negative 2, which will give us negative 10, and 5 by 5, which will give us 25. So our answer would have been negative 10, 25. I hope you get the idea now. All right. So we can do a lot of evaluations here. Unfortunately, we cannot solve these questions, but if we had A as 1 on 3, B as 2 on negative 1, and C as 0, 3, we could do a lot of evaluations. You can add A to B, take C from B, take 2B from A, add A to B to C, and a whole lot of different manipulations. Since you can add, subtract, and multiply a scalar, the scalars are these negative 2 and 3 and negative 2. Since we can do all of those things, we can do all of this summation. And then on the other side, we are required to find the magnitude. That's the reason for these two lines. So when you have found the vector itself, then you can say this squared plus this squared square root. And your answers will look like this. This is where we bring our class, our revision class today, to an end. We have not exhausted all there is to know about vectors, but you have solved enough for you to be able to tackle a lot of questions. I encourage you to practice as much as you can. Please do not leave it for another day. Do it as quickly as you can. Be confident, work hard on the questions, confront the questions. If you have difficulty, consult a friend, go back, watch the videos again, and it will be on YouTube and on our different social media handles. Watch them and revise. Remember the advice, the admonition from Anita? Revise, revise, and revise again. Don't wait for the night before the paper to try to wrap your head around new concepts. That will be too challenging for you. I wish you all the best as you prepare for the exams. Keep calm. It's going to be fine. Until we meet again, I remain very yours sincerely, Danso. Thanks for the pleasure of your company tonight. Keep learning.